So I'm Carol Willis. I'm the founder, director, and curator of the Skyscraper Museum. And I'm really pleased that we can be here in the cool, lovely meeting space of Thornton Tomasetti, who's one of the engineering firms that is going to be featured in tonight's look across mass timber and a little bit of mass timber history. And my board member, trustee of the Skyscraper Museum, Najee Abood, is over in that corner over there, next to the spread that Thornton Tomasetti has put out for us. So thank you very much for hosting tonight. And it's really a delight to be able to be here and to host a large audience, because I don't know how many of you have been to the museum, to the gallery, to see the exhibition. Great, well, not everybody and not a majority. So this is the exhibition, and I will start my slides, actually. The exhibition, which is Tall Timber, the Future of Cities in Wood, an exhibition that is open on Wednesday through Saturday from noon to 6. Admission is free, so I hope you'll come by as it's convenient. It will be up probably through October, so there's time. This is the last of the lecture series of 8 series that we played out in what we think of as our mass timber semester. Some of those have been held at the museum and have included key voices in the history of the mass timber movement. And I'm going to show you some of the past lecture screens from our website so that I can recap some of the ideas that have been the kind of overarching themes of this program, but that this is the view of the gallery and the installation that includes buildings that cover about the last decade to 12 years of innovations and construction in mass timber by some of the key figures who have also spoken in this program. And the series, which is on our website. So this is the home screen or the landing page on our website for the 8 lecture series. And I encourage you to go there, where all but tonight's lecture, the last, is already there. And so you can recap these various about 1 hour deep dives into the mass timber movement, the mass timber industry, the ideas of biogenic materials, of biophilia, and embodied energy. And some of those lectures, and we began with this one, which was called Bi-Coastal Beginnings, which emphasized in the 2 prize winners in 2014, the firm's Lever Architecture with Thomas Robinson, who was one of the speakers, and Chris Sharples of Shop, who's 475 West 18th Street project. Now, neither of these were ultimately built, but were the winners in the competition that was funded by the Softwood Lumber Board in order to try to incentivize innovation in the mass timber industry. And tonight's lecture will also cover, kind of bracket in our speakers who are here and will speak in order. Eric Karsh, who's here from Vancouver tonight and has worked as a structural engineer with his firm EQUILIBRIUM, and has worked with Michael Green, who gave one of the lectures. You'll see him in a moment in the slide. These 12, 14 years, and so is one of the first people in North America, along with architect Michael Green, to really kind of introduce and insist on mass timber as a material for the future, a technological material for the future. The innovation that was encouraged by the $1.5 million grant by the Softwood Lumber Board for this particular tall wood building prize was to underwrite the testing of the projects that received awards, not to build those buildings. And so the role of government, or quasi-government agencies, in trying to jumpstart the mass timber industry is one of the issues we looked at. Another of, and these are views that were shown in those lectures, including the all-wood building, tall, nine stories, of the Lever Architecture's Framework Project. Let me talk a moment about Michael Green, because in his work with Eric Karsh as his engineer, he's someone, or they are people who from 2012 wrote a paper, a Creative Commons, or a public domain paper, to try to do a state of the art of the knowledge of mass timber, and to advocate, as its title described, the case for tall wood buildings. So height, even though it hasn't been achieved much over these last 10 or 12 years, and our title for tonight's talk is Height and Hybrids. So we are looking specifically at height and how do we go taller? How do we optimize the use in terms of vertical for tall buildings? But we'll also be looking at optimizing the material itself. But that case for tall wood buildings, which Michael and Eric have pursued over these years, takes the idea of multi-stories as an aspect of urban density and climate crisis solutions by building urban density. And that's one of the things we'll also talk about tonight. So this project that Eric will mention was kind of for the Empire State Building in wood, was a get attention sort of effort, and it was covered by someone in this audience at the moment, and did indeed raised a lot of eyebrows. There were other projects that Eric will talk about that advocated for multi-stories. Another one of our pair of speakers in the lecture series spoke specifically about the embodied energy as being what we call the now narrative, and the upfront carbon of the carbon cost of building that exists in the materials on the day that the building opens. And this is an enormously important issue, and one that our speakers all will be talking about tonight. So Eleanor Gansky and David Lewis gave an absolutely spectacular lecture that I encourage you to watch on video, where they talked about life cycle analysis, managed forests, and many other issues, and alternative materials, alternative biogenic materials that are part of the kind of predicate that's necessary in order to be the foundations of talking about taking mass timber to scale as a mass-produced and industrialized product. That we'll be talking about tonight. And so in the lecture, in the exhibition, you see issues about embodied energy. We also had Andrew Waugh, who gave us a background in his earliest work from about 2008 or 9 in Europe, in the UK, London-based multi-story building. And we also had Susan Jones, also from the West Coast in Seattle, who, again, in a wonderful lecture that I encourage you to listen to on our website, talked about her participation in code writing in the ICC code that raised, as you can see in the bottom slide, the approved height by code to 12 stories, and then the dream now is 18 stories, and we're going to be talking about height, especially Alejandro Fernandez from the Chicago office of Thornton Tomasetti will be our third speaker. And then in between, we have Benton Johnson from SOM, also from the Chicago office. And I acknowledge our carbon footprint for transportation for this evening is fairly egregious, but the important point is that we're all gathered here together to spread the message and to understand and to meet each other and kind of reinforce the bonds of community of the mass timber movement. So I'm going to hand this over to Eric. I think the longer introduction that we do, I forgot to mention Daniel Safarik, who is here also from Chicago, from the Council on Tall Buildings and Urban Habitat, where Daniel has been the editor on a series of publications like this one right here. The first of their two, well, they're technical manuals called Tall Timber, Mass Timber, and High-Rise Buildings. And Daniel has been very involved throughout these past about 5 years in the CTBUH's initiative to run conferences and publish papers, and then these technical manuals. They were behind the exhibition that was actually started in Chicago at the Chicago Architecture Center called Reframed, which was the foundation for the exhibition, which is now at the Skyscraper Museum. So Daniel is going to do a presentation that summarizes kind of what has happened since about 2020, and when the CTBUH began to pay special attention to mass timber, and then moderate the Q&A that we have after. So, and because I didn't want to forget to do this, I'm going to hold up a membership form for the Skyscraper Museum that I hope some of you will consider. Are there people who have been to or observe or listened to on our website more than one of the lectures tonight, or we have a lot of newcomers? Okay, so a lot of people, and as well as newcomers, thank you very much. Well, I hope that you support this effort, which we would like to continue in other lecture series. The work of putting on programs like this is a lot of work, and the museum has many other missions and initiatives where we devote our time, especially to history. And so we thought that bringing a history to the mass timber movement was an important effort on our part in order to kind of get to understand the dynamic of change, but now to also see where it's going from here. So that's the purpose of our program tonight. So let me just mention that as a profile of Eric, and I'll introduce each of these in between their talks, that Eric Karsh began his structural engineering career in Ottawa in 1987, and in 1998 founded EQUILIBRIUM Consulting in Vancouver. Eric is a leader in the mass timber engineering and construction and sustainability focused design. He's the co-author with Michael Green of The Case for Tallwood Buildings, which spurred global discussions on the topic of timber high-rise of 20 and 30 stories in seismic zones. He's a fellow of a bunch of places and the owner of a BC Passive House, a prefabricator of wood-based high energy efficiency building systems. So Eric.
Thanks, Carol. Everybody can hear me well. So exciting to be here. I'm always jumping at the opportunity to come to New York, and it's great to see some friends in the room. I was a bit ambitious with the number of slides that I picked, so I'm going to jump right into it. So as Carol mentioned, EQUILIBRIUM is a Canadian firm with the headquarters in Vancouver. We've been involved in wood since the very beginning, and we've tried to push innovation in timber construction since the very beginning. And we have probably done well over 1,000 heavy timber projects. We were the first to do CLT in North America with a couple of projects in 2007, the Osprey House and a single family home. And to make sure everybody understands the distinction, heavy timber is referring to post and beam, and mass timber refers to panel construction. We now have offices in 3 locations. Vancouver is the head office. We have about 18 or 20 people there. We have a small growing office in Atlanta and a small growing office in Paris, France. Because we do wood, because we've been experts in wood since the beginning, we've had the opportunity to work on a very wide variety of project types. I think Andrew made a similar comment. The timber specialty has brought us to work on all kinds of projects and all kinds of scales, from single family homes to airports, museum, university buildings, office, multi-residential. This adventure started for me in 1998. the year that we started the office. We didn't have any money, but we spent a little bit that we had to go to a conference in Montreux, Switzerland. It was my first timber conference because my career in the past had been mostly doing steel and concrete buildings. And it completely changed my career. The keynote speaker was a French engineer by the name of Dominique Calvi, a very dramatic fellow, as many French people are. And he just got on the stage and boomed that he was going to build the Tower of the Earth, which was going to highlight the turn of the millennium and was going to be built in Paris near the Eiffel Tower. It was going to be 200 meters tall, and the main shaft was going to be built out of glulam, of 8 4-foot by 4-foot glulam elements. It died a very, very quick political death about a week afterwards. There was a lot of opposition to another crazy government-funded project, which the French take issue with, and the project was never built. But what this did for me is to show me that timber had become a high-tech material officially. And that was in large part due to a couple of things. One is Julius Natterer going to a young mechanical engineer named Hans Hundiger, who had just graduated, and he was designing forestry equipment for his family, and he convinced him to design a robot that could cut structural size timbers. And so he invented the K1, and then shortly after that, the K2. He sold thousands of them, and the rest is history. I'm sure you've heard of Hundiger equipment by now. The accuracy that these machines brought to the manufacturing process for the fabrication timber process allowed us to rethink the way of how we design wood. It allows us to develop all kinds of really high performance connection systems, allowed us to develop connection systems that required accuracy without the labor intensive requirements that come with doing it by hand. And for us anyway, it completely changed the way we looked at timber design. And a good example of that is the project, the first US project actually that we did. We were hired as specialty engineers to re-engineer the roof of the Raleigh-Durham Airport, which we did with a German connection system. That redesign allowed us to save about $1.5 million on a $7 million contract and bring the project on budget. You see here the main terminal of the airport. But also the ability to do complex shapes with CNC equipment made it possible for us to design, again, as specialty engineers, the Galleria Italia at the Art Gallery of Ontario, which is a Frank Gehry project. And you can't see it very well here, but every element in this facade is at a slightly different angle, and all the connections are different, and there was hundreds of them. So again, using CNC's capabilities to simplify the manufacturing process was key to bring this project into being. You see here a view of the Galleria Italia from the interior. And I love showing this picture because this is a museum of art, and yet people are sitting down to look at the structure, which is very gratifying for a structure. But the big change that probably impacted the discussion that we're having today was the advent of mass timber. So the idea that we could manufacture very large wood panels, and when we talk about mass timber, we're not just talking about CLT, we're talking about any engineered wood product that is made in panel form. And the idea of mass timber is the construction system, putting buildings together using large panel products. All that technology kind of gelled and came together in one pivotal project for us, the Earth Sciences at the University of British Columbia in Vancouver, which was a demonstration project funded by the BC government. We could not get CLT in the province yet. So we decided to build the floors out of LSL panels, but because they're limited to 3.5 inches in depth, we had to make them concrete composite. So this is one of the test panels at UBC with 4 inches of concrete and acoustic separation and a 3.5 inch LSL panel, which allowed us to leave the structure exposed. But by the time we got to the roof, Structurelam started producing its first CLT panels, and we were really crossing our fingers that that would happen. So we were able to build a roof and the canopy that wraps around most of the buildings in CLT. But the most challenging element in the building, technically speaking, was what we call the flying stair, which is built out of 10.5-inch glulam on the flat, and it's completely cantilevered. So it's only attached to the floors. There are no cables that you don't see in the image here that are tying the stair to the roof or connections to the columns behind the stair. It's completely cantilevered from the floors. And the connection technologies that I was mentioning before and the ability to manufacture to high accuracy was key in making this stair possible. What you see here is the HSK system, which is a perforated plate connector that is glued into the wood and gives you a very, very rigid connection, which you, of course, need to do a cantilevered stair. So here's a view of the completed structure without the finishes. I have to say, standing at the top of it, I thought nobody's going to want to use this thing. I found it a little bit scary and thought anybody who realizes that this is a wood stair isn't going to want to use it. That was not the case. It turns out the average building user doesn't question the engineer's work, which was good news. So it is in that context that when Michael proposed that we get a small grant to write this case for tall wood, that we approached the challenge of building tall wood buildings, with all that technology and innovation, 15 years of innovation that we had gone through. And, I told Michael, we can do this. But it started as a 12-story building. And if you watch Michael's talk, he mentioned that. And then he jumped directly to 30, but we were at 20 for a little while after he came back from Japan and saw a pagoda that was about 12 stories tall. He said, we got to do 20. And then it became 30 when he went in Australia and was interviewed by a journalist. And then the next day, he was in the Vancouver paper that we were building a 30-story building. And Michael made it sound like it took us a week to figure it out and had a solution for the 30-story building. But from the engineer standpoint, it was a lot more complicated than that. I walked around Vancouver and counted balconies for months trying to wrap my head around the idea that we were going to do a 30-story building, a timber building at some point. But from the architect's perspective, it was a piece of cake. In any case, we developed a system, and we were committed to not just doing the gravity system in wood. We wanted to do the lateral system mostly out of wood. So we developed this, what I would call a CLT shear wall and steel link beams, ductile link beam system, because we're in a high seismic zone for up to 12 stories. And then we developed an exoskeleton equivalent for the higher buildings. And it worked really well. The system has never been used in a real building, as far as I know, but it was tested at UBC and peer reviewed and could be used. But this was the engineer's solution behind the idea of doing a 30-story timber building at the time. This inspired the province of British Columbia to fund a demonstration project called the Wood Innovation Design Center, located in a small town in northern BC called Prince George. Not a very tall building, but it was the tallest all-wood building at the time in 2012, modern all-wood building at about 100 feet. And this is a 3D image that MGA developed to explain the integration of services. Because it was a demonstration building, we wanted to show as much of the structure as possible. So we were looking for clever ways to hide services in a corrugated CLT floor plate, which you see here. And this timber can be built through the winter. And this was the first project in North America to have an all CLT core. Not the highest seismic zone in BC, but still a seismically active zone. And we managed to do the entire building, including the lateral system, out of CLT. There's a view of the lobby, and you see here the underside of this corrugated floor with accessible panels to access services. and then the exterior of the building, which you also saw in Michael's presentation. But then this brought us to a marketing exercise for a company in Finland called Metsä Wood. They make Kerto Q LVL. They wanted us to redesign the Empire State Building out of wood, or find a way to show that it was possible. So we came up with the idea of using shear walls on either side of the 72 elevator banks. So that gave us a 220-foot long shear wall at the base. And then in the opposite direction, we basically went the way that the real building is built, using moment frames. And moment frames in timber are difficult to do. And there's always the issue of creep and in wood and shrinkage. So we had the idea of using a system that was first used in New Zealand, using post-tensioning cables inside of hollow caissons. And we would have had in real life to figure out clever ways to deal with that shrinkage at the column lines, but we did a very simple model and concluded that it was absolutely possible with 5-foot by 6-foot LVL columns at the base. So here's our marketing image, which you've seen probably a few times by now. Another tall wood project with Shigeru Ban in Vancouver. This is called Terrace House. It is right next to the Terrace House building by Arthur Erickson. And Shigeru Ban's idea was to have a concrete structure that matched the concrete structure that is adjacent to it, and then do the rest in timber. Unfortunately, the developer ran out of money, sold the project, and my understanding is that this project right now is going to be built entirely out of concrete. But it got through permitting, and the city of Vancouver approved an 8-story on top of 11-story concrete building. We were invited in 2018 for a competition in Paris. This is the project. It's 1.5 million square feet. We won the competition. There are 6 architects on the project, including Michael Green, who's got the two tallest towers in the middle, and one on the right-hand side by Kengo Kuma, who we helped with engineering. The project has yet to go ahead, but like I said, we won the competition, so we're hoping to go ahead with this project at some point. This is a 26-story tower, which is going to be a concrete core and timber gravity system. So this competition brought us to bid on other projects in France. This one we won the year after and actually got to build it. It's a school board office building. It's 9 stories on top. It's 9 stories in total, including about 1.5 stories of concrete. And what is interesting about this is that it is a dual lamppost and beam, but for cost reasons, we use a very, very thin precast plank for the deck. It's 50 millimeters thick, so 2 inches. And we have a concrete topping for acoustic on top of that. And that project was just topped up about 3 months ago. We kept doing projects in France, so we now have an office of 4 full-time engineers in our Paris office, and are doing other projects. This one is a 350,000 square foot office building, which is currently in construction. This one is in Madison, Wisconsin. It's the first neutral project tower, which is 3 + 11, so 11 stories of timber. And that one also just got completed, the structure. In this one, we have a hybrid steel post and beam, which are all integrated into the partitions. It's multi-residential. And the idea was that we were going to hide all the column and beam elements in the partitions. But the CLT we were hoping was going to be partially exposed. I'm not sure the developer is going to win that battle. And I need to wrap up. This is Google, which we've just recently been allowed to show the first Google office building. 185,000 square feet, 5-story. It's not a tall building, but representative of the potential for mass timber in the market. Like Carol is waving at me. The lateral system is BRBs, which is completely independent of the gravity system, which allowed us to leave it exposed, avoiding intermittent pain. We focused on wood-to-wood connections, trying to avoid steel in the connections. Yeah. So just to wrap up, I didn't talk about the environmental impact of our buildings, but I do think, as Andrew pointed out, that there's a significant opportunity in doing horizontal or vertical expansions and reusing existing structures, either for the expansion itself or for recladding. I think mass timber envelopes are a good way to incorporate significant amounts of buildings in our buildings moving forward. So I apologize if I went a little over my time.
I'll introduce Benton Johnson, who's a structural engineer and a principal at SOM's Chicago office, where he leads the firm's Timber Tower Research Project, a multi-year initiative involving full-scale structural, fire, and acoustics testing of mass timber systems. His work has advanced hybrid mass timber systems, such as the timber concrete composite floors through testing, and he's going to show you this, so I won't say that anymore. But Ben is a passionate advocate for hybrid systems, and he is somebody who had opened my eyes early on in his participation in the 2014 Timber Tower study. That again is one of the 10-year-old projects that really seriously considered how we can bring height into the mass timber movement, and so he wants to, I asked him to talk about that as well as some of his lower rise, more recent work.
Good. Awesome. Well, thanks for that introduction. I put a little title on this because as we were getting ready for this presentation, there was new data, coming out, and thinking about what was the value of hybrid timber buildings. What are you trying to put out there? What are the goals of these things? And for me, I'll get into some of the rationale for why I got into timber construction, but it really was about a climate emergency and thinking about making peace with what you're trying to do to help combat that. So as we were getting ready for this this presentation, we were looking at some of the the global warming data here, and 2024 was terrible year. It's way off the charts. But it's something we've had our eye on for a long time. And so when the Timber Tower Research Project came out in 2013, I've got a little arrow, pointed over there for where we were at that point. And so from our perspective, or from my perspective, I really went to timber construction because of the sustainability of it. I didn't have any really formal training when it came to timber construction. I got the intensity from seeing data like this in different presentations. Phil Enquist was an urban planning partner at SOM for a long time, and he had a lot of great graphics that would spur people to action. And so with the Timber Tower project, really it was trying to think about what is the best and fastest way that we can make a difference in this issue. And this is one of these amazing graphs that was a real eye-opener the first time I saw it. So this is a graph of human population, and to think what that's doing, the planet starting over here at 10,000 BCE, going all the way over, and you can see where zero's at, and then right as the Industrial Revolution happens, it's hitting a ramp and it's going straight up, right? And so thinking about what that impact has been, and really the climate change as a result of it. And so thinking about where is that construction going to happen in the future? So this photograph was taken when the John Hancock Center was under construction back in 1970, had about 3.6 billion people. Since that, now in 2024, we've just cracked 8. We're at 8.1 billion people. And the verticality of that line, we're going to hit one more module of that, up to about 12 billion people. So the amount of construction that it takes to house those people, to put roofs over heads, and to look at where all that population happened, it's happening in cities. And so it wasn't really our goal to look at buildings of this height in terms of practical standpoint. The Timber Tower project was based on this project that was a predecessor to the Trust 2 moving forward. So the question is, how are we going to manage climate change, and how are you going to do it You're going to do it by meeting people in the cities where the population growth is happening. The challenge with that, of course, is the taller that we build, the more materials it takes to build, and the more embodied carbon it takes as well. These are actual built buildings, little data points, and you can actually fit a trend line to that. And you can say, well, if I'm going to build a new building at 500 foot tall, I can go over to the line and pick it out and tell you what the pounds per square foot of that building is, and I can tell you what the carbon footprint of that building. So we know the taller we build, the more intense our structures become, the more material they require. So it's a big ask. You want to bring timber into the city because that's where the population is growing and that's where the buildings are being built, but they're also more intense. And so as we looked at different solutions to meet that criteria, we reimagined the DeWitt Chestnut as a modern timber building. And so to do that, we really thought there were a couple of things that we wanted to be able to achieve. Number one was longevity. Building a building that is going to be obsolete and not occupied is a bad investment because you lock in all that embodied carbon into a building that's half empty. So doing long spans, clear spans to be able to get all the gravity load onto the lateral load resisting system, but also to improve the longevity of the building was key. And we studied this as an all timber building and what our solutions were at a concrete building. But what we find is that the hybrid solution, what was actually most efficient to be able to support that building. And so from that, what we took away was that if you're going to try to make the biggest possible difference, you want to use systems that can be competitive and buildings that are going to have longevity to them. But we also recognize that about 65 or 75% of all the material and embodied carbon was in the floor plate. So we started asking ourselves, if we look at a spectrum of buildings, what is really going to move the needle? So on the left-hand side, you have an all-concrete building. On the right-hand side, you have an all-timber building. And in between, you have all these different options, like option 2, which is a concrete frame with leave-in-place timber formwork. Option 3, which is a composite timber frame and a concrete core, still mostly timber. And then option 4 is, composite timber floor with a timber core. And so our big takeaway from this is, no matter what you're trying to do, I'm trying to sell you a timber floor. You want a timber building? Let's put a timber floor in there. You want to do a steel building? Let's put a timber floor in there. You want to do a concrete building? Let's put a timber floor in there. Because that's where you get the biggest bang for your buck, and that's how you can get speed to market as quickly as possible. And so we did this testing protocol, this testing program in Oregon State, referenced a lot of the work that was done at UBC with all the slip modulus that we're going through here. And what we brought to the table on this was actually using continuity over supports and actually using those rigid connections that concrete can bring to actually expand the floor system's capabilities. So this is 5-ply CLT with 2¼ inches concrete, which can make a 24-foot span. Get those column-free spaces, get those larger flexible spaces that people are going to want to occupy for a long time. And then as part of this, keeping things open sourced, because if you're interested in the sustainability of it, you need to make it available. So we published a report on this with actually blending the US methods and the European methods for timber concrete composite, really as a tech note to start the conversation in the US about using these systems. And all the while we're doing this, we're also, of course, often and designing buildings. So this is the United Nations in Geneva, and we're doing their expansion of their office. You can see it in the foreground there with the green roofs. It included the renovation of the existing building and then the expansion. So the United Nations, their goals are going to be as sustainable as possible, lower the embodied carbon footprint, lower the operational carbon footprint, and that was our mission headed out. So it's an office building that tries to, make peace with the surrounds. It finds itself into the hills. It cascades up. It doesn't try to peek out above the trees because sight lines are important there and enjoying the nature. But it's also human scale. It's got a lot of individual spaces that you can go and reflect on. And I love this photo because now you can see up into the building and you can see that timber concrete composite structure that was used. This is an interior photograph of the project. And what we actually found is that, to achieve those kind of clear spans, again, as United Nations, they're going to be using this building for a long time. You want to be able to adjust those floor plates over time. But what they also wanted to do was have very high energy performing systems, all passive systems, so radiant heating and radiant cooling, and to put that into the slabs. So we also used, precast concrete slabs, 2 inches thick, have a bunch of, coils in there that can do heating and cooling. And this is a great example to say, if you want to get that high performing energy system, if we were to use timber and a concrete slab over it, that timber deck would actually insulate and prevent you from doing the passive cooling as that cooling wants to drop through the slab. And so that actually using a timber building would actually be in a direct conflict with that mission. So by achieving this timber concrete composite, we can get the long open spans and achieve all of the embodied carbon and sustainability goals that we're trying to look at. Now that system could be stacked up to a tall building, but we want to look a little bit more towards North America here with the County Office Building 3 in San Mateo. This building is now complete and getting moved in. And so this project is located in Redwood City, and it's very, very high seismic. The San Andreas Fault is right there next to it. And there were real questions about efficiency, seismic resilience, and really making a statement about California's positions and the county's positions around sustainability. And so contending with that high seismicity is something that you're always trying to deal with when you're looking at a timber structure. So breaking that building apart, the main components were 5 levels of office for the county employees up above, but then this main feature, which is the actual chambers in the lower level, we had to create a very long span to be able to house meetings there. And because of the high seismicity, we ended up using buckling restrained braces. It's an R value of 8, so you absolutely minimize the seismic forces. One of the things that I found so interesting about trying to do these timber buildings is that if you have a lightweight timber system, you're in good shape because the seismic forces are low. But then if you use CLT shear walls, your R factor is equally as low. So your seismic forces end up being about the same as a steel building because you don't have that ductility. So for this project, we located 4 different cores with buckling restrained braces, the highest level of ductility that the code recognizes, so that we can make best use of that lightweight timber system. And these are a couple of drawings of the floor section. And so for us, what we wanted to do was, again, create those long open spans. So we designed the building around shipping lengths. We said, if we're going to have a 65-foot maximum length, we're going to design these bars that are 65 feet long, place a single support in the middle, and have the beams run past the columns. So that they have a continuous span and can make a 32-foot lease span work, which is pretty reasonably large for a timber building. And then the other issue is that when you run into that buckling restrained core, how do you actually make a diaphragm connection? How do you create that rigidity in there? And what we found is that to maintain the depth of the timber beam, by actually using a heavy steel connection into that steel core, you could maintain the depth while also creating a strong seismic connection. So there's this interplay of systems when you're looking at hybrid construction. And so this is the construction as it goes up. The nice thing about the steel cores is they can rise, as fast as the timber. I mean, the timber was right behind them. So there was some argument about pick time and all those things. But this type of system that can stack up, there's really no limit to the height. So when we're talking about 18 stories and taller buildings, it's really about getting the functional spaces correct and being able to detail for all of the necessary fire ratings. Once you achieve that, then when you start stacking it up, you're in good shape for what the code is kind of intending right now. And so this is the long span system there with the 32-foot clear lease depth, and you can see the timber beams that are connecting into those BRB cores. And so by doing that, we were able to minimize the foundation demands and to really minimize all of the costs associated with that. I like this photo here because it's the long transfer beam that was necessary over the chambers to allow for those big meetings. And so the nice thing about hybrid construction and height is you kind of have this extra tool in your tool pouch, right? If you need a big transfer beam, you've got a steel guy on site. If you need a big transfer A-frame, you've got a concrete guy on site that can allow you to do those things. It gives you an extra gear, an extra out as you go through. So there's the building topped up and going forward. So this is a very hybrid building, but you could continue to stack that up until code limits. You might want to make some adjustments about floor plates and things like that. But all the systems, all the kit apart is right there, and it gets you over the finish line sooner. So I wanted to end on kind of like one other thing that we're pushing forward on, which is this issue of the 5-ply cross-laminated timber. I think it's too much CLT. It's too much timber. Most buildings don't need that because they're going to end up using a concrete topping slab on it or for acoustics anyways. So on the left-hand side, you can see the typical section because the California Fire Marshal wouldn't let us do timber concrete composites. You've got your traditional layup. Most timber buildings have about that amount of timber consumption on the floor. But if you were to make that concrete topping slab composite, we could actually reduce that CLT from 5-ply down to 3-ply CLTs, meaning for the amount of timber in 2 COB3s, you could actually build 3. And when we're living in a world where we have finite amount of timber that can be extracted from the forest, this allows us to stretch our buck further. It allows us to get more timber buildings out there, offset more, carbon intensive concrete construction to achieve that ultimate goal, which is to reduce the carbon footprint. And so we've continued on. These are some recent testing photos where we're looking at some TCC behavior and some fancy connectors in there that we're trying to develop and bring to market. And so we're believers in it. We've been at it for a long time, and it all starts and finishes with these floor systems. Thank you.
Alejandro Fernandez is our next up. He's vice president at Thornton Tomasetti, Chicago's office, as part of the building structure practice at TT. And he was involved in the design, structural design of Ascent in Milwaukee, which is currently the world's tallest mass timber building. So he's going to represent height as well as TT. And Alejandro, take it over.
Wonderful. Thank you so much. Thank you, Carol. Thank you, Eric and Benton, for these presentations. It's super interesting to see all these timber projects brought in together. And isn't that on?
No.
Oh, sorry. I see what you mean. Thank you. So what I want to show you now is a little story of 3 buildings that describe a trajectory that we have had at Thornton Tomasetti when we went from research to building the building that Carl is talking about, which is currently the tallest mass timber building in the world, and then a newer building that we're doing that is going to beat the record of Ascent. So the first project is River Beach, and it's actually a project that has shown up already in another of the presentations earlier in this program. This was a project that University of Cambridge promoted. And University of Cambridge, they had a budget for investigation. They were trying to do research on mass timber buildings, and they approached a number of companies to try to push the limits of mass timber construction. And by doing that, identified the areas where research was needed. So one of the companies that they reached out was Perkins & Will and Thornton Tomasetti. Thornton Tomasetti, if you're not familiar with it, it has a lot of experience in tall buildings, including some of the tallest buildings in the world. So we were well positioned to design something like this. Now, once we start doing this, the first step was trying to understand what are the uniqueness of timber construction, especially when you're pushing it to these heights, right? How much timber is a great material, but it's softer than steel and concrete. And because that's the case, then you're going to need more material. So what can you do to start to have more material, but without impacting so much, having these huge members, walls, and maybe you're going to start, first of all, making it more efficient and pushing the material towards the facades. Second thing is let's have a lot of material by creating windows. So maybe we can use these diagrids and then making use of the mass timber panels, so trying to have CLT shear walls. So it was a combination of all these things that came to this structure that became interesting. Now, a lot of it had to do with connections. That's one of the parts that we realized that it was a key item for these buildings, and there was a lot of research. Carl showed earlier a few of these connections, so how we're trying to join these pieces. It also unveiled one of the potentials of mass timber, which is prefabrication. And together with prefabrication, there is the potential for modularity. And how can we maybe start building our cities outside of the city and just bring these mass timber volumes that are just stacked very quickly on the city and allow us to build faster and in areas that maybe are not so easy to build. But the most important thing of River Beach to me is it created these renders. It started unveiling to the world the possibilities of mass timber buildings. And this got published, everyone got very excited. And there was publications all around the world about this building. And you start to see the warmth of a mass timber building, this connection with nature, how it creates a completely unique experience. And out of these renders, one day in the office, we got a call from a developer in Milwaukee. And this developer had a land a plot of land in Milwaukee for a number of years. This was the third attempt at the property. And they had actually been able to zone a building that was 35 stories tall, but the numbers didn't work. Milwaukee is a concrete market, it's super cheap, and they kept trying with concrete. The numbers didn't make sense. And suddenly they saw those renders of River Beach, and they saw an opportunity to create a market differentiator. And with a little bit of a smaller building that they were trying to do in concrete, suddenly the numbers start making sense. Now they can charge Chicago rents in a suburban, in an area that is further out, like Milwaukee, and they can start making the numbers work. So Ascent is a 25-story building. It's currently the tallest mass timber building in the world. It has a 7-story podium and 18 stories of timber above. And here I can show you a little, well, hopefully we can show a little construction sequence. So this is the building where you can see there's a concrete podium. The bottom is a parking, and on top we have residential units. So as in any building, everything starts with the foundations. It's Milwaukee, so they go very deep, and then you start with the traditional construction. Now you can see that at the top of the podium, there is a transfer system because the grid of timber is a little bit denser than the grid of concrete. And then the building has glulam columns, glulam beams, and on top of this structure, we have CLT panels. And this building, it ended up having 18 stories of mass timber construction on top of the podium, and it was built at 1 story per week. Now, in order to do this building, one of the things that we had to do is we were doing a new construction system at the time. Like nowadays, we have a lot of mass timber buildings, and each day is becoming more and more new, but especially for these heights, all the partners that were involved in the project had to get adapted. So we had to make sure that our mechanical engineers adapted to timber, which is a material that is going to move much more than a traditional concrete building. This building vertically, it moved in construction like a 60-story concrete building. So all those movements had to be integrated in the structure, and there were like uniqueness with all these. There was also a lot of detailing that had to happen to truly maximize the potential for prefabrication and optimize the construction process. Now, the good news is the project moved forward, even if it was right at the beginning of COVID. We're bringing all the timber from Europe, and there was like all the Canal Suez blocking the whole world. But everything came on time, and in a matter of months, all the timber was erected. And you can see here a picture of the construction. It's glulam columns, glulam beams, CLT. It's a very clean construction. Everything comes prefabricated. There is very little work. There is only a crew of 12 people to build this 20,000 square feet per floor. Now, and they create these amazing spaces, right? Like you start exposing the timber. So this developer wanted to expose timber. So it was not only about building in timber, but being able to expose the timber. And we got very lucky because the city of Milwaukee was actually very receptive to approve the building through a variance process. So they let us allow, and we ended up exposing about 50% of the timber in the building was exposed. Now, a few weeks ago, 2 weeks ago, we actually submitted the foundation permit for the next iteration of this building. So that building was done with Muran Enterprises was the developer, and Corban Associates was the architect. The new iteration was with the same construction company, which is C.D. Smith, but it's a different developer. It's a neutral project, which is actually the same developer that Eric was showing for Breakers Place. but now they're going to a new height. The ascent was 25 stories. Now we're rising all the way to 35 stories. And it's pushing the standards in different ways, including bringing the passive house certification to a high-rise building. So it's going to be a very unique building. It's not only breaking the height of mass timber construction, but it's also becoming a very sustainable building with their systems. Now, what we have done in this process is because we were using the same contractor as we had in Ascent, we looked back and said, what can we do better than what we did in Ascent? And we realized that on a traditional timber system, you have your concrete topping that Benton and Eric were showing, then you have your CLT slab, and below that you have your glulam beams, right? That ends up being quite a big structural depth. So the other item you have is when you go to these heights, you end up having to create the connection between your beams and your columns, have to have a certain fire rating, typically 2 to 3 hours. So all those connections become expensive. So there was a number of things that push us to rethink our mass timber system. And instead of doing a timber system, we went into a hybrid system. So now we're creating this system where we have these concrete beams that are supporting CLT slabs. So I'll do a very quick construction sequence. We have the glulam columns that support these prefabricated C-shapes that are temporarily short. And then on top of that, we put our glulam or CLT panels. So you can have a continuous mass timber surface. And then on top of that, we put a concrete topping that it forms these concrete beams. So now we don't need to do any sort of complicated connectors. And then we can automatically build the next floor. So this system has actually become very cost competitive, especially in markets where concrete is very competitive. And the combination of both, it's opening a lot of possibilities. Now we can do long spans, we can do higher loads like labs. We're seeing a lot of opportunities with this system, while we're keeping the aesthetics of mass timber construction. You still have your ceilings, your beams, your glulam columns that preserve that aesthetic. And then this is the top floor where we have these skylights, and we're just start bringing this connection. Like, I think to me, this starts talking about that connection of timber, right? That how it connects you back to nature in the city space. Thank you so much.
Thank you so much, Alejandro. For a few minutes, Daniel Safarik is going to present summarize the research about these past 4 or 5 years that the Council on Tall Buildings and Urban Habitat has been involved with. Dan is the Director of Research and Thought Leadership at CTBUH, and he's co-authored, I held it up before, numerous of the Council's technical guides, including this tall timber, mass timber and high-rise buildings. He's the editor-in-chief from 2013 to the present, and the director also of the China office. Spanning the world, Daniel. So Dan is in your next slide. Oh, you've got it. Okay. Is going to give a little recap of some of the work that they've done, and then he's going to be the moderator for the brief discussion that we'll do. Dan.
Thank you. Thanks so much, Carol, and to the previous presenters, and I'm enjoying talking with you in a few minutes. Okay, so I'll be brief. Basically, the Council on Tall Buildings and Urban Habitat, as you might guess from the name, is the organization that measures tall buildings. We're the ones who say, you've got the tallest building in X, Y, or Z, and we set the criteria for doing that. We were founded in 1969. Only very recently have we become the Council on Tall Buildings and Timber Habitat. And that's largely due to a lot of the people who are in this room. And we owe them a big credit. So the history of the world's tallest timber building is actually rather short. We trace it back to the beginning of the introduction of CLT in Europe, and specifically in London with the Stadthaus back in 2009. And you see we quickly bring it all the way up to the ascent, which was just shown. It's quite an acceleration over the period of time that we're talking about here, much faster than the growth path of the traditional concrete and steel high-rise buildings. Distribution-wise, it's still, because of the implementation of the technology in Europe, specifically Austria, and then the Scandinavian countries, there's quite a bit more historical mass of these projects in Europe. But as you've seen, a lot of the projects that are now breaking the records are here in North America. And it's also very popular in Oceania. And in fact, possibly the next tallest building after the Edison is completed will be a 40-plus story office building in Sydney, Australia. So it really is becoming a global phenomenon. We conducted a tall timber global audit, and effectively, we sort of set the limit at 8 stories and up. Typically, if you go below 8 stories, you're talking about other types of construction that are more commonplace and not strictly mass timber, but more like the kind of frame construction that we're used to seeing in suburban conditions. So we decided not to include those because there's billions of those. But when we got into the tall timber, basically going from the mass timber qualification, you see that a lot of them are residential, a lot of them are in Europe, and a lot of them are all timber. That is starting to change, though. You start to see more hybrids coming in the taller we get. And there's a lot of good reasons for that, which we've already alluded to in some of these project examples. We got funded by a research project with the U.S. Forest Service and the Binational Softwood Lumber Council to develop an awareness and educational program about tall timber. And basically this involved a set of case studies, and it also involved basically what I would call 10 to 12 advice columns from some of the leading experts in tall timber, considerations that you should undertake if you are serious about developing a tall timber building. Some of those folks are also in the audience tonight. This is the book. Carol already did me the favor of putting it up in the physical space, so I'll just show it on the screen. It is quite substantial, and we're very proud of it, and it is available for sale on our website. We also conducted a symposium as the timbers hybrid question became more acute. This resulted in a great gathering, and including some of the people who are also in this room again tonight at the Crown Hall, not a timber building, but a very famous building by Mies van der Rohe at IIT in Chicago. That was about 2 years ago, and that was the kickoff for this project, which is the future potential of steel timber hybrid buildings specifically. Actually got the steel and the timber industries together to talk about this concept. And there's some footnotes to that, but the long story short is that we are going to produce a really good report showing the best examples of case studies with the timber steel hybrid combination. So just to give you an idea of how we classify these structures, an all timber structure is one that's considered to be well, basically all the major structural forces are handled by timber. So a good example would be this building in Norway, formerly the tallest timber building in the world, called Mjøsternet. This was kind of a one-off project by someone who wanted to prove that this was possible. It probably helped that they were next to a lake that had a lot of fire extinguishing water capability. And it's pretty much in the middle of nowhere. If you've never heard of Brumunddal, Norway, you're probably not alone. Probably most Norwegians have not heard of Brumunddal. It's not a very big city, so the risk was fairly low, but it's a fantastic project. Concrete timber hybrid structures are similar to the ones that you've been seeing in the previous projects, where basically all the above ground vertical floor spanning and the lateral force resisting structural elements are constructed in timber, concrete, or a combination of the two. And what we're increasingly finding is, again, the higher you go, the more you need a hybrid structure of some kind. The steel timber hybrid structures are really good in those seismic regions. These are two examples from the same project in the Victoria, British Columbia, where there was a real need to account for seismic forces that timber alone probably wouldn't be able to convince the authorities that this was a good idea. So the buckling restrained brace or a concentric framed brace are presented as the central core and stabilizing factors in these buildings, which account for the circuitous forces that are enacted upon buildings during seismic events, which timber is not necessarily best equipped to do by itself. And then, of course, you have the ultimate combination, which is the concrete steel timber hybrid structure. What we're looking at here is actually quite old. It's from 2003, and it was really a trailblazing project. It's called De Carol Dorman. It's a extension of a 2 or 3 story 1940s art moderne department store, which was much beloved in the community because it was one of the first buildings that was built after Rotterdam was pretty much leveled in World War II. And the only way to build a proper extension on top of this was to use light gauge steel. And actually, I'm not even sure if we would call this mass timber today. It's a kind of an LVL hybrid. They came up with this bespoke system that proved out that this can be done. And now there's a lot of more developed systems for doing this. So, I mean, the basic reason we would use hybrids kind of come down to a couple of optimization factors. One is the greater spanning capability compared with an all timber system. Obviously, you can go long distances with timber, but the cost that exacts is that you then start to have deeper and deeper beams, which become impractical. You can have more efficient structural sizes for both the columns and the spanning elements. These are two approximately similar bearing capabilities, with a steel column and a timber column, and you can see how much bigger the all timber column actually is. You can obviously achieve greater heights with steel's greater compressive strength. This is an example of a building that really took that example of the floors being the main factor in the weight of the building and the amount of carbon that's invested. This was a hybrid tower that proposed going all the way up to 103 stories with a concrete steel timber hybrid system. The big operative difference there being that the floors were CLT. Greater beam span, the depth ratio provides more efficient floor-to-floor heights, again, avoiding those deep floor beams. And of course, better options for lateral restraint systems in your taller buildings than a conventional timber system. This is that project I was mentioning in Australia for the software company Atlassian, which is just getting out of the ground now. Ductility is another concept which has been explained quite thoroughly by our engineering compatriots here, so I won't try to over-explain that myself. But you still have the maximization of timber's biophilic properties. So you're not necessarily dependent on it for all the structural loads, but you are able to then display the structural timber that you do have in an aesthetically pleasing way. I happen to think that the intersection of timber and steel is a great thing to be looking at from an aesthetic standpoint, as well as a structural efficiency. So as part of this project that we developed as the outcome of this grant, we did a tall timber website, which is updated consistently, unlike a big massive book that you can only put out a couple times every couple of years. The Tall Timber website is updated constantly. As soon as a building enters our database that is tagged timber, it goes on this website. That is talltimbercenter.com. And we encourage everyone who thinks that this is worthwhile research to join us, become a member of CTBUH. We have good gatherings, and a lot of people in this organization, or rather in this room, can testify to that. I hope I've kept it reasonably brief. Now I'm going to step into the moderating role. Thank you. Okay, so I'd like to begin with the word that we saw on the screen right at the beginning of this whole discussion, which is optimization. It's a kind of maybe a clinical sounding word, but I think it really addresses some of the existential issues that we as an industry, and more importantly, we as a planet face. So I would ask each of you in succession, what do you think that that hybrid timber systems optimize for? What do you think is the key problem that they solve, both conceptually as far as world spanning issues are concerned, but also in your own practices with respect to your projects? start with Benton.
Yeah, well, I think that a lot of times when we're looking at these timber buildings, you're trying to do things that are light impact, light on the foundations, light on the carbon impact. And so I find that a lot of times when we're trying to, optimize using timber, it's all about reduction, right? You're trying to minimize seismic forces, minimize the demand on your foundations, minimize your carbon footprint. And so it depends on the particular project. I mean, we talked about some, projects where you're trying to add floors on top of existing structures. And of course, that makes a lot of sense. So with hybrid construction, really it's all about getting the materials to work harder by allowing them to do what they do best naturally. And you find that with the hybrid solutions that have been discussed tonight, related to the engineering performance as well as the sustainability performance.
Excellent. Eric?
Yeah. So I'll start with a comment that we can certainly achieve acoustic separations or acoustic performance requirements with non-concrete or non-cementitious products. It's been done in Europe. But in my experience, it typically comes with a premium. And so we find ourselves achieving our acoustic requirement by the addition of a concrete topping. In Canada, we don't use gypcrete, so typically this is a standard concrete topping we're talking about. And so what we've tried to do is to make that concrete topping do as many things as possible. So it's our acoustic separation to begin with that typically sets its minimum thickness. And then if we're in a high seismic zone, we're going to rely on it as a diaphragm because it's cheaper to do that than to get the CLT to be the diaphragm because of the connection cost. It's maybe your floor finish. Anyway, we try to make the materials that we have to use for economy work in as many ways as possible. The other thing that I would add is that we have to point out that it is better to use a hybrid system that may not be as clean from a carbon standpoint than to go concrete. So if going hybrid is what we need to do to bring the costs in line with what the developer had in mind, we'll do it to get some wood in the building. And ultimately, we're going to, most buildings we do now are still custom. We haven't found that system in mass timber that is truly repeatable. And we're still kind of feeling our way around, but I think eventually we're going to find what that is and we're going to repeat it. And that system may not be a pure CLT or heavy timber building system. It will likely be a hybrid system.
Yeah, I think the other aspect is for a number of years we're talking about mass timber buildings. We're typically talking about residential buildings or office buildings. Now, as we're getting more accustomed to the use of mass timber, we're starting to push the limits. You have seen a few examples today. We're trying to go higher, but we're also starting to try to push for longer spans. We're pushing for higher levels, higher loads. Now there's talk about building labs for universities with mass timber. There is people that are trying to do these Class A offices that are spanning 50 feet with mass timber buildings. So as we go into these new unexplored territories, then we need to find the right materials that we were talking about. And though we can probably do it with mass timber, is really mass timber the appropriate material. And especially, I think I like that you brought the economics of it, right? Like when you start thinking that this project, at the end of the day, they have to be affordable. And can we meet the goals of the project? Can we meet the sustainability, but also the aesthetics, and still do a building that is affordable? I think that's where these hybrid systems start becoming very powerful.
Thank you. I guess another question would be, optimization isn't something that just happens in a vacuum that structural engineers get to solve the problem and say, well, we figured out the most structurally optimal solution, the most economical. There's also the very real question of the economic realities on the ground that the developer's facing and the government, the code or the zoning that applies to this situation. What were some of the biggest obstacles that you think that are preventing mass timber or mass timber hybrid construction in high-rise format from becoming a mainstream phenomenon? And how would you know when it was a mainstream phenomenon? Like what would success look like on scale?
Well, I think success on scale would be you go to a job site and the contractor says, well, I've always been doing it this way, right? Because that's the classic line when you go and talk about any kind of thing. Well, I've always been doing it this way. So I think when you show up to a CLT job site and they start saying, well, I've always been doing it this way, that's when you'll know it's mainstream, because you've got a crew that's come back and has some history to,
Yeah, I think code-wise we've made huge progress. I mean, in most places in North America, we were limited to 4 stories in timber until very recently. And the US being as dynamic and efficient as it typically is, went to 18 stories before Canada got to it, even though we've been doing it a little bit longer. So the US, I think, in my mind right now, is leading the way from a code standpoint as far as making it possible to push the limit. France, which is politically very motivated to do wood, just recently took a step back and said, we're going to encapsulate everything if you don't sprinkler the building. Because then the French don't want sprinklers, so they're wrapping up all their timber right now, which is terrible. But as I pointed out before, I think we're still looking for that truly repeatable, efficient system that the contractors are going to get to know well, that the developers are going to get to know well, are going to be priced quickly, understood, and will become truly repeatable. And companies like Rotoglass, for example, are developing products very quickly that are bringing us closer and closer to that point. And I think that point is not that far off. We're going to find a truly repeatable system and that's going to be pretty soon.
Yeah, the other item I would add to you guys, I completely agree, but I would say manufacturing and procurement. I think we're in a very great path. It has taken a number of years, but when we were doing Ascent, we ended up procuring from Europe because the volume of timber we're trying to procure will have pretty much like occupied a whole factory for a whole year, and there was a huge risk, right? Now we have some very big players in North America. The number of companies that are fabricating mass timber has increased dramatically. You were mentioning Rotoglass, the number of connector fasteners and beam-to-column connections. The number of manufacturers that are doing that has also increased a lot. So I think we still have to catch up. We were talking earlier before the meeting about, before the panel, about how Europe is still way more automatized. So I think, they've been doing it for longer, so it makes sense. The US is catching up, and North America in general is catching up very, very fast, but I think we still need to catch up a little bit. The manufacturing has to increase, the number of players is going to increase, and then we're going to get into the more of the mainstream that you're talking about.
Right. And clearly, one of the most important things about all of this is the level of embodied carbon that goes into it. Do you think that we're at a point where there's enough public communication about the importance of doing that a developer could go out and say to the public or say to their investors, I want to limit the amount of embodied carbon because that's important? Or do you think they need to also make the leasing velocity argument, in order to convince someone to fund their mass timber high-rise project?
Yeah, it's kind of a difficult one, right? Because the whole LEED system that we have for scoring buildings, and like the Department of Energy for the longest time, focused on energy conservation, reducing the energy consumption of buildings, retrofitting old buildings to make them more efficient, and all these things. And there's been a huge push for that, which is great because it has immediate impacts on the grid, you know, and how much power draw you're having and energy mixes and all these other kind of things. But those government incentives for low embodied carbon just aren't really there, and they're not really there very well in the lead scoring systems either, or pick whatever sustainable system you want, right? You can get a point here or a point here if you do an LCA, but I don't think that, you know, governments or code bodies or other industry organizations really recognize the importance of it enough, because if you could jump to a, you know, lead platinum by reducing your embodied carbon by 50%, then that would really change how people see it and how they would approach it. And so I think that it's right now, it's kind of people don't really know what to do with it. And they're like, okay, well, that's good. That's less is better, good. But there's not sort of an end product that you can point to that says this is a tangible reason why I want to do it, other than just, you know, being a good, you know, neighbor and steward.
Yeah, and Andrew Waugh actually did a really good job of explaining how we've pretty well tackled the energy efficiency side of things, the operational side of things, to the point where now the embodied energy is in the structure, mostly. So that's what we have to tackle next, and of course government regulations are going to have to come in to incentivize people to do that. But that's something that we're aware is going to be coming up, and I think that's going to help developing the mass timber industry very quickly.
I would add that I think the bright thing that's happening right now, I believe, is the private corporations, especially all these big players, right? They have self-imposed themselves very strict limits on their carbon emissions, and they are really looking into. They have started to understand that embodied carbon, the upfront carbon, it's a big part of it. It's not only the efficiency of the building, making sure that all systems are very efficient, but like what are we putting into our building and how much emissions are we creating with that. So all these big corporations, now they have high goals and they are pushing, this is one of the reasons for them to push for mass timber. If you think about it, for a number of years after COVID, we were like running into shortages of steel. Why was that? It was like all these warehouses and data centers that were being built around, right? So if all these big actors start embracing mass timber, and now they have a financial and a public relationship interest on pushing mass timber, that's going to be a big driver for the whole industry to start adapting and to start incorporating mass timber in our design. So I think we're going to see more and more.
Yeah, I'd also like to add that it's not like we're hanging back and waiting for some, you know, credits to come our way before they're doing the right thing. You know, SE 2050 is out there. You know, I think all of our firms are signatories about getting to zero embodied carbon footprint by the year 2050. Part of that comes with changes to the grid as well as changing your designs. We all have to put out, you know, embodied carbon action plans and all these kinds of things. So we're doing the right thing, but for it to take it to that next level, it can't just be engineers talking to engineers about what these things are. People need to be able to see it and feel it and experience it in their projects through whatever kind of benefits and other things you can bring to the table now.
Last question. For all of you, what do you think is going to be the next big moment in hybrid timber construction that will surprise the general population as well as the AEC community?
I think there are a number of things that are starting to be exciting, right? There is a lot of research happening right now in Europe with different species. Like, for example, there's a lot with bamboo. Bamboo can grow very fast, it's very strong. I mean, when we're looking at these tall buildings, like Edison is 35 stories, like you end up having like very big columns at the base of the building. So can we get materials that are actually stronger, but are still timber? That would be really exciting. I think there's another set of research that is happening, like, for example, there is this, I think it's a university or private corporation that is looking into reusing the dust of timber. And how can we use this dust to start like 3D printing buildings? So I think there are a number of things that are happening that have the potential to revolutionize how we see the timber buildings right now.
Yeah, Michael Green talked about the fifth, what he calls the fifth material, which is along that line. Personally, what I think I'd like to see is more reuse. The prefab prefabrication capabilities that we're developing in the mass timber supply chain right now are perfectly adapted to reusing existing structures by either expanding them vertically, horizontally, or simply recladding them in prefabricated mass timber panels that don't need, that can be pre-finished in the shop and then installed without scaffolding, you know, with pressure gasket systems. And you know, it's been done a little bit in Europe. We tried to do it here in North America with limited success. But there's photographic equipment now that can produce a very accurate digitized 3D model of an existing structure that can then be used in the prefabrication process to prefabricate very accurately a structure that will attach to an existing concrete structure. And we all know that concrete structures can be all over the place. So that technology, which we're developing right now in the mass timber world, can be used in the reuse market. And I think that's the next logical step. There's a concern about forests also being not being able to keep up. So I think reuse is something that we have to.
Yeah, I think there's a lot of material research that's happening. I think one of the challenges with the hybrid timber construction is how do you deal with temporary conditions, to avoid shoring. When you're doing steel construction, you just avoid shoring like anything else. But oftentimes when you're using these concrete topping slabs, it's kind of too heavy to be able to support that in a temporary condition. It deflects too much in that. So I think that you're going to see solutions that are out there that help combat that, whether it be cambering of CLTs. There's a lot of really interesting research that comes into saying, I'm going to build a CLT, but I'm going to take the bottom layer, I'm going to over dry it so it's going to expand, and I'm going to take the lowest layer and I'm going to make sure it's really wet so it shrinks. And then by doing that differential drying and shrinking, you can actually distort the shape of timber components as they acclimate. So I think there's going to be this whole kind of side material science dealt around how do we make this hybrid construction that much more efficient, because we've watched the steel industry do it for decades and decades and decades. And I think the timber industry is going to follow suit.
Thank you all.
All right, well, let me just say a last word in this last, at least this section of the series of our attention to mass timber, that I'm really delighted that we could have an engineer's evening, because the sobriety and the practicality that you bring to the issue, as well as the optimism about looking forward, is really a wonderful way to focus this technical discussion, but to put it in the context of the invention that has been represented across the decades or so that you've all been practicing. So you've really brought the history, a short history of mass timber into focus and condensed it for us tonight and topped off the series by doing that. So I thank you all for being here, and for the Chicagoans and the Pacific Northwest for coming to New York. I hope we'll catch up to your history, and I hope we'll expand the movement as well. So thank you all for being here. Thank you for coming tonight.